Hello everyone, welcome to this course on dynamic time warping with Python from a data science perspective. So, dynamic time warping is a very useful method when you want to analyze temporal sequences of data. In other words, data which is collected over a fixed frequency of time, and you have multiple subsequences or multiple sequences uh, of time series data or temporal sequences of data that you want to compare and contrast with. For example, if you want to calculate the similarity or dissimilarity between two or more temporal sequences of data, dynamic time warping is very useful for that task. So in this lecture, I will describe what is dynamic time warping, what is the algorithm behind this method, and also what is the mathematical formulation that is involved in this algorithm, and the overall optimization problem as well. I will discuss those things separately. And then in the end, I will describe the advantages and the limitations and the key features of this method. And then towards the end of this lecture, I will do a demo in Python in a Jupyter notebook where I will implement a dynamic time warping in a real time series data and show you how this method is so useful for that task. So before I start, let me give you some background about the data that is on which this method is applied. It's a time series data, and time series data is now everywhere in every field, whether it's stock market data, whether it's healthcare data, or it's sensor data, or supply chain data, or networking data, any data that has temporal sequences, or which means time series sequences. And when you want to analyze that data to generate insights, patterns, and trends and relationships, you need to use this method called dynamic time warping. And this method, it empowers data scientists or any data science professional to unravel patterns in time series data. So basically, this is an essential method in your data science toolkit. So let's start. So the agenda of this course is that I will describe dynamic time warping in time series data. Then I will describe alignment based metrics. Then I will describe what is dynamic time warping, then understanding dynamic time warping, and then I will describe the principles behind dynamic time warping. I will also show some applications of dynamic time warping, and then I will show how does dynamic time warping work. Then I will show you DTW or dynamic time warping. It's the shortcut for that. DTW mathematical formulation. What is the mathematical equations or mathematical formulation involved in this algorithm? Then I will show you the optimization problem, the overall optimization problem behind DTW. Then I will show you the summary of DTW steps, the key features of DTW, the advantages of dynamic time warping, and the limitations of DTW, the enhancements and variations of DTW, and the key features of DTW algorithm. And in the end, then I will do a demo of the DTW implementation in Python. So basically, this is one of the most comprehensive tutorials on dynamic time warping. So make sure you attend the skills and the concepts that I describe here, because they will be very useful in 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 our data science professional career. All right, so let's dive in. So dynamic time warping in time series data. Dynamic time warping is a way of comparing two or more temporal sequences that don't perfectly sync up through mathematics, or which means they may or may not be equal in length. One of the sequence can have different timestamps, and the other one can have totally different timestamps, and they may not be equal in length altogether. The process of DTW is commonly used in data mining, to measure the distance between two time series. It is also a useful method in fields like financial markets and speech recognition. So, for speech recognition, when we have multiple sequences of spoken words and we want to, for example, identify who is speaking, let's say we want to compare that, then we can use this method of dynamic time warping. For example, when we want to say some sentences or awaken our gadgets at home like Amazon Alexa, so we can we can say the same sentences at different speeds. So the Amazon Alexa, under its hood, it does use dynamic time warping to compare uh, who is speaking. So dynamic time warping is used to compare similarity or calculate distance between two arrays or time series with different lengths. Dynamic time warping is an algorithm designed to compare two sequences and measure their similarity by finding an optimal alignment between them. This is achieved by warping the time axis of the sequences to align them in a way that minimizes the distance between corresponding points. And that distance is usually the Euclidean distance. I'm sure all of you have studied in at least early schooling the Pythagoras theorem. So the principles of Pythagoras theorem is used in calculating Euclidean distance, and we usually use that distance when we are implementing dynamic time warping. For instance, consider two sequences representing the same speech sound but spoken at different speeds. So the DTW method can stretch or compress the time axis to align the sequences, and that allows for a meaningful comparison between or among those sequences that we are comparing for similarity or dissimilarity. So dynamic time warping is a powerful algorithm used in time series analysis to measure the similarity between two time sequences. And unlike traditional distance metrics like Euclidean distance, dynamic time warping can handle sequences of different lengths. It can align sequences that can be out of sync or that can have different time periods. And that's how it makes useful to compare those sequences in fields like speech recognition, gesture analysis, and finance. Alright, so what is alignment-based metrics? So this graph shows you have Euclidean distance on left and dynamic time warping on your right. So in Euclidean distance, there's always one-to-one mapping, which means one timestamp, one value of each timestamp is measured with its respective timestamp in the other sequence. However, dynamic time warping, you can match one to many or many to one, which means one variable or one value in one time sequence can have its multiple matches in the other sequence that we are comparing with. And this allows to compare and contrast with more similarity measures that basically allows us to gather more insights and more patterns that we can generate by using dynamic time warping. So here we are computing similarity between two time series using either Euclidean distance on your left side or dynamic time warping on your right side, which is an instance of alignment-based metric that we will present in more details later in this tutorial. In both cases, the return similarity is the sum of distances between matched features. Here matches are represented by gray lines and the distance associated to a match between each point of the two sequences of series X and the jth feature in series X bar, which is the other sequence, and the distance is called xi, xj, which is the distance among all of the points in both of these sequences that we are comparing. So the orange are the two sequences that we are comparing. So basically note how DTW matches distinctive patterns of time series, and then that's how it generates the similarity assessments uh, as compared to when we just use Euclidean distance that matches timestamps regardless of the feature's values. So basically, dynamic time warping is equivalent to minimizing Euclidean distance between aligned time series under all admissible temporal sequences or timestamps. Alright, so continued here again. What is dynamic time warping? Well, in time series data analysis, dynamic time warping is an algorithm for measuring similarity between two temporal sequences, which may vary in speed. For instance, similarities in walking could be detected using dynamic time warping, even if one person was walking faster than the other, or if there were accelerations or deaccelerations during the course of an observation. Dynamic time warping, or DTW, has been applied to temporal sequences of video, audio, and graphics data. Indeed, any data that can be turned into a one-dimensional sequence can be analyzed with DTW. A well-known application has been automatic speech recognition to cope with different speaking speeds. Other applications include speaker recognition and online signature recognition. It can also be used in partial shape matching applications. Dynamic time warping is used to compare similarity or calculate distance between two arrays over time series with different lengths. Dynamic time warping is a family of algorithms which compute local stretch or compression to apply to the time axis of two time series in order to optimally map one query onto the other reference. Dynamic time warping outputs the remaining cumulative distance between the two sequences that we are comparing, and then mapping itself using the warping function that it calculates between the two sequences that we are comparing. So basically, dynamic time warping is widely used. For example, classification and clustering tasks in econometrics, when we want to associate values to each clusters or classify the values by assigning them some labels. So there we can use dynamic time warping, and it's very useful for those tasks. Or in chemometrics and general time series data mining. So dynamic time warping between two piecewise linear functions is shown on the right side graph. The dotted line uh, in the top diagram illustrates the time warp relationship, like how the values in one sequence are related to the values in the other sequence. And again, we can use one to many and many to one mapping. Notice that several points in the lower function are mapped to one point in the upper function, and vice versa. And the diagram, which is blue and red in color on the right side and bottom part, it's once you have calculated the warping function between the two sequences that you're analyzing. That's how it looks like. Understanding dynamic time warping. One of the most salient uses of dynamic time warping is in speech recognition, determining whether one phrase matches another, even if the phrase is spoken faster or slower than its comparison. You can imagine that this comes in handy to identify the wake words used to activate your Google Home or Amazon Alexa device when you instruct the device to do something, and then it identifies your speech, and in the back end it applies the dynamic time warping algorithm to identify. Dynamic time warping is a useful, powerful technique that can be applied across many different domains. Once you understand the concept of dynamic time warping, it is easy to see examples of its applications in daily life and its exciting future applications. Consider the following use cases. In financial markets, when we are comparing stock market data over similar time frames, even if they do not match up perfectly. For example, comparing monthly trading data for February 28 days and March 31 days. Though the length is different of February and March, you can still compare the stocks for these 2 months of different companies using dynamic time warping. For wearable fitness trackers, when we want to more accurately calculate walkers' speed and number of steps, even if their speed varied over time. Another use case is for route calculation, when we want to calculate more accurate information about drivers' estimated time of arrival. If we know something about their driving habits, for example, they drive quickly on straightaways, but they take more time than average to make left turns. So for these use cases, dynamic time warping is applied, and the algorithm is very useful to basically calculate the things that we want to compare or calculate for each of these use cases. What are the principles of dynamic time warping? Well, the objective of time series comparison methods is to produce a distance metric between two input time series sequences. The similarity or dissimilarity of two time series is typically calculated by converting the data into vectors and then calculate the Euclidean distance between those points in vector space. Dynamic time warping is a seminal time series comparison technique that has been used for speech and word recognition since the 1970s with sound waves as the source. So this method is used a lot in engineering as well for different tasks like word recognition, speech recognition, gesture analysis, and now as the time series data is becoming more and more popular or more applicable, so this method is definitely a must to understand and to learn to analyze the data. So in general, dynamic time warping is a method that calculates an optimal match between two given sequences like time series data with certain restrictions and rules. So the rules are: every index from the first sequence must be matched with one or more indices from the other sequence, and vice versa. The first index from the first sequence must be matched with the first index from the other sequence, but it does not have to be its only match because there can be one to many matches. The last index from the first sequence must be matched with the last index from the other sequence, and it does not have to be its only match, again because of one to one, many or many to one mapping. So the mapping of the indices from the first sequence to indices from the other sequence must be monotonically increasing, and vice versa. For example, if j is greater than I are indices from the first sequence, then there must not be two indices L is greater than K in the other sequence, such that index I is matched with index L and index J is matched with index K, and vice versa. So what are the applications of dynamic time warping? Well, it's used in speech recognition, where DTW can determine if one phrase matches another, even if the phrases are spoken at different speeds. This is useful for identifying wake words for devices like Google Home and Amazon Alexa. It's used in financial markets, where DTW can compare stock trading data over similar time frames, even if the data does not match up perfectly. DTW is used in video, audio, and graphics data, where it can analyze temporal sequences of any data, which means data collected over time, and that can be turned into a one-dimensional sequence, meaning that the data has one variable. in one sequence. DTW can also be used for satellite image time series data classification, where it can be used to provide an overview of the state of rangelands and cropland in semi-arid regions. In medical diagnosis, DTW is used to align and compare biological signals such as ECG or EEG readings, helping in the diagnosis of conditions by comparing patient data with reference models. So, if doctors want to ascertain if a patient has a certain disease and they have some benchmarks which provide an indication of a disease or not a disease, then they can compare the patient's ECG or EEG readings with those benchmarks using dynamic time warping, and based on that they can confirm if a patient has a disease or not. So it's very useful for medical diagnosis as well. In gesture recognition, DTW helps align different gestures for comparison, even when performed at different speeds or with slight variations. DTW has several advantages over other methods, including it is accurate for two sequences with different lengths, it is fast to calculate, and it is not sensitive to time delays or uneven sampling time. Well, how does dynamic time warping work? The algorithm in the algorithm there are several steps that constitute the algorithm. So the step one is where we construct distance metrics. So the first step in DTW involves constructing a distance metric between two sequences, or if you have more for multi-sequenced multi-dynamic time warping. So in this case, there are two sequences, so we use them. So each element of the metric represents the distance, typically Euclidean distance, between corresponding points in the two sequences. Once we construct distance metrics, then we construct cost metrics and calculate accumulated cost. So next, in this method, a cost matrix is created by accumulating the minimum distances from the start of the sequences to the current period. This accumulated cost represents the optimal path's cumulative distance up to that point. Third step is optimal path finding, where the optimal alignment path is found by tracking back from the last element in the cost matrix to the first element. This path represents the best alignment between two sequences by minimizing the total distance. So that's the optimal path which minimizes the total distance. And in step 4, we find the warping path, which shows how one sequence can be warped, stretched, or compressed along the time axis to best match the other sequence, which can be in greater or less length than this sequence, because the two sequences can be out of sync, it can be of different length. So warping path shows you how the stretching and compression is done when we are finding the best match between those sequences using DTW. So what is the DTW mathematical formulation? Well, if you have two sequences A, which is A underscore 1, A underscore 2, and up till A underscore n, and B is the other sequence which has elements B underscore 1, B underscore 2, up till B underscore m, and where A underscore I in sequence A and B underscore j in sequence B are elements of the sequences A and B respectively, DTW computes the minimum cumulative distance between them. So then the step 1, when we found the cost matrix, where we define a cost matrix C of size n times m, where Ci, g represents the cost or distance of aligning A underscore I in sequence A with B underscore j in sequence B. The cost is typically calculated using a distance metric, such as the Euclidean distance. And the formula for that is C I comma j equals to the distance method calculated between AI and BJ. And then we take a modulus of that or absolute value of that so that the distance is always positive. Then we find the accumulated cost matrix where we construct an accumulated cost matrix D where each element D, I, j represents the minimum cumulative cost to align the first three elements of A uh, with the first j elements of B. And the step 2 and step 3 are the methods used for that construction of accumulated cost matrix. In part 3, we have the boundary conditions which are initialized like D11 equals to C11, and you can read that in detail. So that's how we define the mathematical formulation. And finally, in step 4, we find the optimal warping path, which is a sequence of metrics that indicates the minimum distance between the two sequences, and it is found by backtracking from distance n comma m to distance 1 comma 1 by following the minimum cost direction at each step. So the DTW optimization problem is where we find the similarity between two time series. For example, you have two time series x and y of respective lengths n and m. Here all elements of xi and yj are assumed to lie in the same d-dimensional space. So in tslearn is a package in Python programming language which is used for data science tasks and which is the focus in this lecture as well. So when we are using tslearn package from Python, such time series would be represented as arrays of shapes n, d and m, d. And then we can calculate DTW by using the following code. So here you are seeing we from tslearn.matrix we imported DTW and DTW path, and then we applied DTW to the x and y sequence, and then we calculated DTW score. So this is like with Python and R, you have all the packages available to you where you can easily find these variables. And under the hood in the back end, the way the algorithm works is what I have been showing you in the previous slides, the mathematical formulation. But it's good to understand how it works, so you know what is happening. But you can very easily calculate these things by using these packages in Python. So the DTW optimization problem is, for example, you have x and y sequences, and the optimization problem is that you want to minimize the distance among all the elements of those two sequences. So DTW xy is equals to minimum square root in the summation of all the distances between all the elements of x and y, where dxi and yj is the distance between points xi from series A and yj from series B, and then the sum is taken over all points ij in the optimal path alignment process. So the properties are defined here, you can read that. And so basically the path can be seen as a temporal alignment of time series, such as the Euclidean distance between aligned or reassembled time series. And when that path is minimal or that distance is minimal, that's what the temporal alignment is. So the following image shows the DTW path in white for a given pair of time series, x and y in this case, on top of the cross similarity matrix that stores the values of distances among all the elements of sequence x and sequence y. So the bottom diagram shows you the end result of applying dynamic time warping, where you find the best possible path or the warping path that is found by minimizing the distances among all the elements of the two sequences, and that's the best path between those two time series, or the best similarity measure between those two sequences. Summary of dynamic time warping steps. In step 1, you calculate the cost matrix Ci, j. Then you compute the accumulated cost matrix Di, j. And in step 3, you find the optimal warping path by backtracking from dn, m to d1, 1. And in step 4, which is the final step, you find the dynamic time warping distance, or the best path, or the warping path, which is dn, m. What are the key features of dynamic time warping method? It allows handling of non-linear alignments. Because dynamic time warping can handle non-linear alignments between sequences, which is crucial when comparing sequences that may be out of sync or have different lengths. It provides robustness to temporal variations. Unlike simple distance measures, dynamic time warping is robust to variations in speed or timing within the sequences, making it ideal for applications like speech or motion analysis. Dynamic time warping provides flexibility because it can be applied to any time series data, regardless of the domain, as long as the sequences can be represented numerically. So as long as you have numbers or values collected over fixed frequency of time, you can apply dynamic time warping to compare and contrast those time series data. What are the advantages of dynamic time warping? It allows handling of different lengths of time series data. Because dynamic time warping can compare sequences of different length, it makes it versatile for various applications where time series data may not be perfectly aligned. It provides alignment of complex sequences because dynamic time warping is particularly useful in aligning complex sequences that may have local shifts in time, such as varying speech rates or irregular patterns in financial data. So if you have two time series data, and one is, for example, collected hourly, which has hourly frequency, and the other one is daily or uh, 10 minutes or any other time series data. Basically, if the frequency of in time interval is different, you can still use dynamic time warping to compare and contrast those time series data. Because in conventional method, when you're using data mining to compare those time series, you need to have similar frequency of time interval if you want to compare. But with dynamic time warping, it's possible to compare even different frequencies of timestamps in the data to analyze and to compare. Dynamic time warping is effective in noisy environments because its ability to warp time allows to effectively compare sequences even in noisy environments where traditional methods might fail. What are the limitations of dynamic time warping? Number one is computational complexity. Because dynamic time warping can be computationally intensive, especially with long sequences, uh, as the algorithm's complexity is quadratic in the length of those sequences. There's overwarping because without constraints, dynamic time warping might overwarp sequences, leading to unnatural alignments. So, to avoid that problem, we use constraints like Sacco-Chiba bands, which can mitigate the overwarping issue when we are using dynamic time warping. Dynamic time warping is sensitive to scaling because it does not inherently handle differences in amplitude or scaling between sequences. So pre-processing like normalization is often required. And there's another very popular method that we use to avoid this problem. It's called fast Fourier transform. So when you have time series data which has a lot of noise or a lot of jumps or a lot of peaks or lots of uneven patterns, and you want to minimize that noise. For example, in sensor data, there's a lot of noise always, and we want to smoothen that data before applying dynamic time warping. So we use this method called fast Fourier transform before to smooth out those sequences before applying dynamic time warping. What are the enhancements and variations of dynamic time warping? Number one is global path constraints. So constraints like Sacco-Chiba band or Itakura parallelogram can be applied to limit the warping path. Uh, so it allows to reduce computational cost and to prevent overwarping. Multi-dimensional or dynamic time warping, or MDDTW. It is used for complex data with multiple dimensions. For example, in motion capture data, MDDTW can be used to align and compare multi-dimensional time series. Or multi-dimensional time series basically where you have multiple variables in each sequence and you want to compare those variables with similar other sequences or any other sequence which can also have multiple variables, then you can use MDDTW method. Weighted dynamic time warping is applied using different weights to different parts of the sequence, and this allows for more flexible and more context-aware comparisons. So you can uh, provide more emphasis to some parts of the sequence by applying different weights than the other parts of the sequences, because you know those parts of the sequences can have more trends or more patterns that you want to analyze. So weighted DTW method can be used for that. What are the key learnings for DTW algorithm? Well, the dynamic time warping method, or DTW, is a good non-parametric algorithm. And by non-parametric, I mean that it learns itself from the data without providing lots of rules. You can use this method by applying it on the data, and then it learns the sequences within that data. And therefore, it is simple to be used because it does not require any parameter tuning. Dynamic time warping is a robust benchmark for time series data classification problems. Well, what are time series classification problems? Well, I have another lecture where I define time series data classification comprehensively, so you can watch that video as well for more information on this topic. Well, dynamic time warping is also computationally expensive. Uh, and in case of known characteristic time scale of a phenomena, example periodicity, well, there is some periodic patterns that happen repetitively in the data. And in case of a specific pattern to classify, dynamic time warping can be used as a starting point for a classification task. For example, if you want to uh, find anomalies in your data, or for anomaly detection, which is one specific use case that you want to do or you want to use on your time series data. So dynamic time warping can be very useful for those tasks. All right, now I will show you how this method, dynamic time warping, is implemented uh, using Python in a Jupyter notebook. So here I created a Jupyter notebook where I implemented this method. So here, first cell, you implemented all the libraries. So I'm fetching some time series data uh, for models like Tesla and Amazon. Um, and there I implemented it. So basically this cell should come here. All right. All right. So I imported all the necessary packages. This Y-Finance package you can use to import stock market data. NumPy is for mathematical uh, calculations. DTA distance is a package in Python from which I can import DTW method to implement dynamic time warping. Then matplotlib is used for plotting. Pandas is the basic package for data mining in Python. Then I have another packages that I'm using here for the analysis. So here I have two example sequences, and I want to calculate DTW distance between those two time series. We have S1 and S2, and I calculated the distance, the DTW distance, by using DTW dot distance, and then I found this value is very low, which means S1 and S2 are quite similar. So I have another two sequences S1 and S2 that I define using NumPy array method, and then I'm finding the best warping path by using the dynamic time warping method between S1 and S2, and then I plotted. So here you can see the top is S1 and the bottom is S2. How best the elements in each of these sequences S1 and S2 are connected. So you can see there's one-to-one mapping and there's one-to-many mapping. For example, the first point in this sequence S2 is connected to 2 points in S1 because that's how they are related. So I find the best warping path using this method. So in the backend, the whole algorithm is being implemented and all the steps are done, but we are using this package, so we are just finding looking at the results. So here is another example where I'm calculating using two synthetic data S1 and S2 by using methods numpy.sine, where I'm creating two sinusoidal graphs curves, and then I'm applying the dynamic time warping method to find the best warping path between S1 and S2. And here I am defining two parameters, window size and PSI size. Then I find the best path between S1 and S2, and here is what I got. S1 is the top and the S2 is on the left side. So this is the best warping path between S1 and S2 using the dynamic time warping. So that's how you find the warping path. So now here is another example. I'm using two stock market data because for stock market data, dynamic time warping is very useful. So I'm fetching time series data using YF package that I imported in the beginning in Python. So we'll fetch historical stock price data for Tesla and Amazon over the past year. So I pulled the data, and then I use the period of 1 year, and then I'm using the closing values for each day, and then we will ensure both time series are of the same length and handle any potential missing data. So in this case, it's not necessary, but I'm trying to make sure that they are of equal length because I want to find how similar they are. Although you can still use dynamic time warping when the length is different, but in this case I'm just making sure both the lengths of Tesla and Amazon stock market data that I just pulled are equal. And if there's any missing data, I'm using fill null method in Python by forward filling the empty spaces. So make sure there are no null values in the data. And then I'm finding them, making sure that they are of equal length. Next, I'm calculating the dynamic time warping distance between the two stock price time series data, which in this case is Tesla and Amazon. And I found that the distance is 690.321 because, and this indicates that they are totally different, quite different. In fact, 690 is a big number. So let's see how different they are. So this is a graph which plots the data. For blue is Tesla and green is Amazon. So you can see just from almost after February 2024 and up till July 2024, there was some similarity. Although there were uneven patterns in Tesla, there were lots of dips, but Amazon was quite stable during that time, and that's the time when both were playing or were operating in the same region and the same price. So there was some sort of similarity, but otherwise they were totally different. This is the last 1 year data, beginning from November 2023 to November 2024, and we calculated the dynamic time warping distance. So the DTW distance of 690.321 between Tesla and Amazon that we calculated just now indicates that the stock price movements of Tesla and Amazon over the past year are somewhat dissimilar. That's because you have such a big number of DTW. And they may share some overall market trends, but the specifics of their price changes, such as the timing and magnitude of increases or decreases, differ significantly. This distance reflects the unique behaviors and market dynamics influencing each company's stock. Alright, in the next example, I am using some synthetic data that I am creating here for time series A and time series B, and I am finding a DTW distance to obtain the warping path between those two sequences. I calculate the similarity score. Here I am plotting the original time series A and B. Then I am finding the shortest path. And here I am doing the point-to-point comparison. Then I'm creating a data frame to display the similarity score and correlation coefficient, and then I'm adding some descriptions, and basically in this part I'm applying the method and storing it in variables called distance, paths, and best path is the warping path. So the result is this. On the left side you have original two time series. Now this is an example where two time series data can be of different length. So you see series A is shorter in length than series B, and you can still apply dynamic time warping. So after applying the method dynamic time warping, we found the shortest path or the best path between those sequences, and the green line is the best path. You can see that x-axis is series A, which is a bigger sequence, and series B is a shorter sequence. So you can see that in some cases one element in series A is connected to multiple elements in series B. For example, this point where you have vertical points on top of each other, this indicates that there is one-to-many mapping. And this is point-to-point comparison after dynamic time warping alignment. So you can see the best warping paths between the elements in the two sequences. And again, there is lots of one-to-many and many-to-one connections happening between series A and series B. And the value that we calculated for DTW similarity score is 0.30, and lower score indicates that there is greater similarity between series A and series B, which you can see yourself that they are quite similar, although one is higher, one is shorter, but the trends are similar. So trend is what we are interested in. So trends are similar in the almost all the time. So the shortest path graph here that he found here is used to visualize the optimal alignment path determined by the DTW algorithm between the two time series. In this path, the shortest path is this one, green one. In shortest path, the horizontal axis is series A and the vertical is the index points in series B. And the green dots that you are seeing here represent the mapping of points from series A to series B that dynamic time warping has found as the best alignment. The line connecting these points demonstrates the sequence in which the points in series A map to points in series B. A step up indicates that a single point in series A corresponds to multiple points in series B. This is the step up, this is the vertical path. Which suggests that in segment series B moves slower or has more details than series A. A step to the right indicates the opposite, where a single point in series B maps to multiple points in series A. As you move this side, the one path corresponds to multiple paths. See, this one point in series B corresponds to multiple points in series A. Because 0 is corresponding to 0 and 2.5 and 5 and up to 6 maybe to series A. So a diagonal move indicates one-to-one mapping, showing that both series progress at the same space. Diagonal is when you are this is the diagonal path. So the point-to-point graph that we have in here, what is the point-to-point graph? Well, it shows the comparison after DTW alignment. It illustrates the actual alignment of the two time series based on the optimal path from dynamic time warping algorithm. Each point in series A, blue line with circles, is connected by a gray line to its corresponding point in series B. Series B is an orange dashed line with crosses here, as determined by dynamic time warping. The direct connections between the points highlight the warping of the time axis and show how specific points in one series align with those in another. For example, a peak in series A may correspond to a peak in series B, even if they occur at different times in the original time series. And that's how you have similar trends in both of them, and that's why you have such a low DTW value score, which means that both of the series A and B are quite similar. This alignment accounts for variations in speed or timing between the series. Basically, it's a visualization of the warping that dynamic time warping suggests for aligning the two sequences. Shorter line indicates closer matches between the series at those points, and longer lines show the stretching that was needed to align them. So a score of 0 here would mean that both series were identical. So we are almost close to 0.30. A score of 1 would mean that they are not similar at all, and anything in between is relative. So scores under 0.5 indicate more similarity, and greater than 0.5 indicate less similarity. So in this case, a score of 0.3 indicates that there is a lot of similarity between series A and series B. So that was the whole demo in dynamic time warping, where I implemented this method in Python and showed you all these examples. This notebook will be available as a link in the description part of this video. I have uploaded all the slides in this notebook as well, so you can use it for reference. Now I'll show you some useful links. So this is the dynamic time warping link where we use tslearn package in Python, and it shows you how this algorithm is used, what is the optimization problem, what is the algorithm, and what are the properties, the constraints, what is soft DTW, and some other examples. So you'll find this link in the end of the slides as well. There's another useful link. It's DTA distance package in Python, from which you can import DTW, and then you can use this method to apply on the data. So this link has useful materials. For example, DTW distance measure between two time series, the complexity and the early stopping, what is DTW tuning, DTW and keep all warping paths method, if you have multiple time series, then how you can apply DTW between multiple time series limited to block and based on shape, multi-dimensional dynamic time warping. Remember we saw a multi-DTW method that I discussed. So this has the implementation of that. And finally, I'll show you how this method, this package is actually installed. So you can use pip install dtw-python to install it in Jupyter Notebook, and you can see this link for more details. All right. Hope you enjoyed and learned a lot in this lecture. Make sure you subscribe to the channel so that you don't miss my upcoming videos on that I'll be preparing on several other topics in data science. So make sure you subscribe and stay connected. Do provide your comments, do like the video, do share the video, and do let me know if there is any improvement or is there any particular thing you want me to include in my future videos. So I'll definitely look at those. Thank you very much, and God bless you all.